Hello and welcome everyone to this video where we'll be starting with the revision of geometry. Now, the main issue that I've had with several students with respect to geometry revision, and whenever they ask me that, sir, can you help me out with geometry? The biggest issue they have is that they say that they don't know what all concepts uh, do they need to familiarize themselves when it comes to the topic of geometry. Right? What all theorems do you need to know? What all concepts? What all formula do you need to know before you jump in to solving geometry questions? And this is what we are going to be actually doing in today's class. I'm going to be calling it Geometry 1, and I'm going to be calling it Theory, because we are not going to solve any questions in this video. The the purpose of this video is to just basically convey whatever concepts and formula are relevant towards geometry, even before we get into the questions. And since geometry is such a vast topic when it comes to the number of formula, number of concepts, number of theorems, corollaries, and all these are concerned, I'm going to break this theory videos down into two parts as well. Today we are going to be dealing with only quadrilaterals and triangles, and we are going to be looking at what all theory, concepts, and formula do we need to be familiarized with even before we start solving the questions. So treat this video as a tool to make notes and create notes of all the concepts and theorems of quadrilaterals and triangles, all of them consolidated together into one single place, which you can refer to when you're solving geometry-based questions. I'm going to keep this video up till CAT, but what I would suggest is that when you switch on this video, take a pen, a notebook, sit, listen to what is happening, and just make a note of everything that's been talked about here. Okay. Also, what I'm trying to do is I'm trying to cover exactly what I feel is relevant towards CAT. I might be conveying a few concepts and formula which will be, beyond what is required for CAT as well. But be rest assured that if you just know these things that I'm talking about here, CAT never asks anything beyond what we are discussing here. It does not require the knowledge of more concepts which are far more advanced than these which we are discussing in today's class. Okay, so without any further ado, let's start with the topic of quadrilaterals, and please be ready to take notes. And pardon my handwriting is very bad, I know that, but I hope that it is legible and everyone can actually understand what I'm writing here. Okay, so quadrilaterals, we all know what are quadrilaterals. Those are any shape which enclose an area using four straight lines. So four straight lines enclosing an area is known as quadrilateral. And there is only one fundamental property of quadrilaterals that you need to remember, which is that sum of the interior angles of a quadrilateral will always be equal to 360 degrees. So this is it. If you know this, this is it that you need to know about general quadrilaterals. Okay. Now beyond this, we will come to the classification of quadrilaterals. Now quadrilaterals can be of several different types, especially based on how many sides are parallel to each other. So if I have to have parallel sides in a quadrilateral, but I want to have the minimum number of sides parallel to each other within a quadrilateral, then that will be two sides, right? So two sides of a quadrilateral are parallel to each other. So I've got one side here and I've got one side here, right? So the remaining two sides are non-parallel. So this is a quadrilateral, and this kind of a quadrilateral in which exactly one pair of opposite sides are parallel to each other is called a trapezium. So what all do we need to understand about trapeziums? These are quadrilaterals in which exactly one pair of opposite sides are parallel to each other, which means that within a trapezium, there is two sets of parallel line and transverse system. So AB and CD are parallel, AD is a transverse, BC is also a transverse. So from the property of basic parallel line and transverse systems, we know that interior adjacent angles will be supplementary. So this angle plus this angle will always be equal to 180 degrees in the case of a trapezium. So this is what is the fundamental property which is true for all trapeziums. Okay. Now, sometimes what happens is, it is possible that I have a trapezium in which the two non-parallel sides are of the same length. So say suppose I have a trapezium like this. Let me erase this properly. I have a trapezium like this. Once again, let me call this ABCD. And suppose in this trapezium, I tell you that AD and BC are equal to each other. Of course, it does not look like that in this figure, but let us suppose that the non-parallel sides of a trapezium are equal in length to each other. Then such a trapezium is called an isosceles trapezium. And property of an isosceles trapezium is that both the angles formed by any one of the parallel sides will be equal to each other. So if I take any one of the parallel sides, if I take the parallel side AB, AB forms two angles, angle A and angle B, these two will be equal to each other. Similarly, CD forms two angles, angle B and angle C, these two will be equal to each other as well, right? So this is the property of all isosceles trapeziums in which the non-parallel sides are equal in length. So this is the first step of a quadrilateral in which exactly one pair of opposite sides are parallel to each other. Second type of a quadrilateral will be, of course, when both pairs of opposite sides are parallel. So I can have a quadrilateral like this, in which I've got these two sides parallel and I have these two sides parallel to each other as well. Then such a quadrilateral is called a parallelogram, right? When both pairs of opposite sides are parallel. So in this figure, ABCD is a parallelogram. So whenever I have a parallelogram, it has got three fundamental properties. Okay. Fundamental properties means opposite sides are equal. That's the first fundamental property. Second fundamental property is opposite angles are equal. And when I say opposite angles, I mean the diagonally opposite angles. Right? And third and final fundamental property is the diagonals of a parallelogram, they bisect each other. Now, one issue that I feel that several students have is with the concept of fundamental properties. So what do I mean by fundamental properties? So when I say that opposite sides of a parallelogram are equal and I call it a fundamental property, that means that if that one property has been satisfied, then the resultant quadrilateral will be a parallelogram. So if a question tells you that in a quadrilateral, both pairs of opposite sides are equal in length, then that is all the evidence that is required to tell us that the resultant quadrilateral will be a parallelogram. Okay. Similarly, if a say question tells you there is a quadrilateral in which the diagonals are bisecting each other, then that means that the resultant quadrilateral will be a parallelogram. Okay. Now the third property says diagonals bisect each other, which means say the two diagonals AC and BD, suppose they are cutting each other at the point O, then O will be the midpoint of both AC as well as BD. This is what this third property implies, that AO will be equal to OC, BO will be equal to OD. This does not imply that AC and BD will be equal. That is not a property of a parallelogram. In a parallelogram, the diagonals need not be of the same length, but there can be a parallelogram in which the diagonals are equal in length. So if there is a special type of a parallelogram in which the diagonals are equal in length, then that kind of a parallelogram is what is called a rectangle. So a rectangle is a special type of a parallelogram in which the diagonals have the same length. So if I have a quadrilateral ABCD and the question says ABCD is a parallelogram in which AC and BD are equal, that means that it is a rectangle. Okay. So that's a property of a rectangle. Diagonals are equal in length. And second property of all rectangles is that, of course, we all know that all the angles are equal as well. So all angles are equal to 90 degrees. Right. So this is the second property of all rectangles. All right. Now, coming back to the property of parallelograms. So parallelograms, I see that the first property says opposite sides are equal, which means the sides which are next to each other, sides which are adjacent to each other, they may be equal, they may not be equal. That is not the property of a parallelogram. But of course, I can draw parallelograms in which all four sides are equal. So if a question tells you specifically that all four sides of a parallelogram are equal in length, then that means that the resultant parallelogram is a rhombus. The question just tells you that all four sides of a parallelogram are equal in length, then that means that this parallelogram ABCD is a rhombus. So rhombus, first thing that we need to remember about rhombus, the first property is that all sides are equal. Second property that we need to remember about rhombus is that the diagonals, we all know this, since school we have studied this, the diagonals, they bisect each other at 90 degree, right? So diagonals bisect at 90 degree. In general parallelograms, they just bisect each other. But specifically in a rhombus, the angle of bisection is equal to 90 degrees. And the third property is that the diagonals of a rhombus are its interior angle bisectors. Okay. So what do I mean by that is that if I take the diagonal AC is going to bisect the angle A and it's also going to bisect the angle C. BD is going to bisect angle B as well as angle D. Okay. The angles of a rhombus are its interior angle bisectors. So rectangles and rhombi are two special types of parallelograms in which, number one, in a rectangle, the diagonals are going to be equal in length and all the angles are equal to 90 degree. And rhombi is a special type of parallelogram in which all sides are equal, diagonals bisect at 90 degree, and diagonals are its interior angle bisectors as well. Okay. Now, apart from these, we all know that the most special type of a parallelogram happens to be the square. Square is the most special parallelogram. Why? Because a square combines the property of a rectangle and a rhombus. If you take rectangle's properties and then to that you add to the property of rhombi, then you get a square. So which means that if a question tells you that there is a rectangle in which the diagonals are equal, or there is a parallelogram in which the diagonals are equal and the diagonals bisect at 90 degrees, that means that the resultant quadrilateral or the resultant parallelogram has to be a square. Right? So all five properties, three properties of rhombi plus two properties of rectangles put together is what will give you a square. So these are the different special types of quadrilaterals that we will deal with in our syllabus, and it's very important to understand that these are their fundamental properties. Okay, if a question tells you that a parallelogram has all four sides equal, I see several students, they assume that this quadrilateral is a square and then they solve the question. But let's understand that just having all sides equal is not a square. All four sides equal plus any one of the properties of rectangle being equal is necessary for a parallelogram to be a square. Okay. So from these relations, the hierarchy between the different types of quadrilaterals should become clear as well. And what is the hierarchy of relations? I can look at the properties and I can say that if I take quadrilaterals, then some of them are trapeziums, some of them are parallelograms, and some of them are just general quadrilaterals. Right? Now, if I take parallelograms, I can say that parallelograms are of several types. Some are rectangles, some are rhombi, and again, some are general parallelograms. And some types of rectangles and some type of rhombi will give you squares. And of course, there are general rectangles and there are general rhombi. So from this hierarchy, we can say that all squares are rectangles, or squares are rhombi, or rhombi are parallelograms, or rectangles are parallelograms, or parallelograms are quadrilaterals, all trapeziums are quadrilaterals. So these say properties of this special type of quadrilaterals tell us their mutual relationship. So if this is clear, then apart from this, there is only one other type of special quadrilateral which is present inside the CAT syllabus and CAT questions, which is a cyclic quadrilateral. The last special type of a quadrilateral is cyclic. So what's a cyclic quadrilateral? Any quadrilateral which can be perfectly inscribed inside a square. Or if a circle, not a square, any quadrilateral which can be perfectly inscribed inside a circle. Or if I can say that if a circle can perfectly circumscribe a quadrilateral, then that quadrilateral will be called a cyclic quadrilateral. Okay. Not all quadrilaterals can be circumscribed by a circle. Only some, say some special ones can. And if a quadrilateral like ABCD can be perfectly circumscribed by a square such that the four vertices of the quadrilateral lie on its circumference, then this kind of a quadrilateral is called a cyclic quadrilateral. And property of a cyclic quadrilateral is opposite angles are supplementary. So if I find the sum of the diagonally opposite angles, then they will add up to 180 degrees. Right? So this is the last special type of a quadrilateral, and this is the only property that is actually required. People actually talk about Ptolemy's theorem with respect to diagonals of a cyclic quadrilateral and all. That is nothing but a theorem of circles, which is then put into cyclic quadrilaterals. So I would not suggest that you learn any more theorems with respect to quadrilaterals than these. Okay. Now that we have looked at classification of quadrilaterals, now one more special case of a quadrilateral I want to talk about here. So for that, say suppose let me draw a random quadrilateral like this. Now if in this random quadrilateral, if I say join the midpoints of the sides, right? If I take the midpoints of the four sides and I join the midpoints of adjacent sides of such a quadrilateral, then I'll get a new quadrilateral, right? So if say the first quadrilateral was ABCD, and the midpoint of AB was P, BC was Q, CD was R, and AD is S, then the second quadrilateral that I'm forming is PQRS. So in such a case, PQRS is referred to as the midpoint quadrilateral of ABCD. Okay, so this is another property which definitely comes in handy in several geometry questions if you have an understanding of a few things about midpoint quadrilaterals. Okay, so midpoint quadrilaterals, let's understand this. Let me represent this by MPQ so that I don't have to write this again and again. So MPQ, first and foremost, you have to understand that an MPQ's area will always be half the parent quadrilateral's area. So in this figure, PQRS's area will always be half of the area of the quadrilateral ABCD. This property comes in handy in solving several mensuration-based questions. Okay. So area of a midpoint quadrilateral will always be half of the area of the parent quadrilateral. That is the first thing to remember. Second thing is there are some special midpoint quadrilateral relations which can also help us solve a few questions. So the first relation for midpoint quadrilateral is if I take a kite, let's also discuss what a kite is while we're on the subject. So a kite is a special type of a parallelogram in which one pair of opposite sides are equal and the second pair of opposite sides are equal to each other, but the two pairs are not equal to each other, not opposite sides. One pair of adjacent sides are equal in length. The second pair of adjacent sides is also equal in length, but these two pairs do not have the same length. So this and this are equal, this and this are equal, then this is a kite. Okay, which means that this cannot be a parallelogram, because in a parallelogram opposite sides have to be equal, which is not true in this case. Second property of kites is that the diagonals of a kite will intersect at right angles. So diagonals will always intersect at right angles. This is a property of a kite. Okay, so this is what a kite is. So midpoint quadrilateral property, if I want to look at, and I can say that midpoint quadrilateral of a kite will be a rectangle. If you join the midpoints of the sides of a kite, you will get a rectangle. Second thing that we have to remember is that a rectangle's midpoint quadrilateral, if I join the midpoints of the sides of a rectangle, I will get a rhombus. Then what do I get if I join the midpoints of the sides of a rhombus? I'll get a rectangle. Similarly, a square's midpoint quadrilateral will be a square. And finally, if I take any random quadrilateral, any randomly shaped quadrilateral like ABCD that I've drawn here, which is not any of the special quadrilaterals that we have, and if I join the midpoints, then I will get a parallelogram. So all midpoint quadrilaterals are parallelograms. Okay, there is this proofs for this. I don't want to get into the details of this, but this you can make a note of as the midpoint quadrilateral properties. Right? So surprisingly, quadrilaterals, that's it. That's about it. That's all that we have to deal with in terms of quadrilaterals. There's nothing more than this that you need to actually make a note of and remember if you want to solve geometry questions in CAT as far as the topic of quadrilaterals is concerned. Right? So now with this out of the way, let's move on to triangles. So triangles, of course, these are much more vast. The topic of triangles is much more vast than the topic of quadrilaterals. So let's sit back and take our time in making notes for this. First thing, we look at fundamental properties of triangles. Definition of triangles, we all know, is it's a geometric shape which is enclosing an area using three straight lines. Right? And fundamental properties also all of us are kind of aware of. I always focus on the knowledge of four fundamental properties that we need to have if we are solving questions based on triangles. Right? First fundamental property we all know for a triangle is that sum of interior angles is 180. All of us know that. Second is, if I take the lengths of the three sides as small a, small b, and small c, then of course sum of two sides of a triangle will be greater than the third side. And as an extension, difference between two sides of a triangle will be less than the third side. Right? This is an inequality-based relations when it comes to triangles. So if you're looking for inequality-based relations, this is the fundamental property of triangles that we will turn to. Okay, this helps us find the range of values of some parameters of triangles if at all it is needed in a question. All right. Next, we all know exterior angle is equal to sum of interior opposite angles. Now, what is an exterior angle? I know all of us know, but I just want to clarify that exterior angle, not just for triangles, but for polygons in general in geometry, exterior angles are angles which are formed by the produced part of a side with an existing side. So if I produce a side BC to the point D, then CD is the produced part of the side BC, and the angle that CD forms with an existing side AC, which is angle ACD, is an exterior angle. And for a triangle, the exterior angle, of course, will be equal to the sum of the interior angles which are opposite to this exterior angle. So angle C will be equal to angle A plus angle B. So that's the third property, third fundamental property of triangles. And the fourth property, fourth basic theorem in triangles is that the side opposite to the greater angle will be greater than the side which is opposite to the lesser angle. Right? So if I say take a triangle in which say angle A is equal to 60 degrees. Okay. Angle C is suppose given to us as 27 degrees. So between these two, 60 degrees is a greater angle and 27 degree is a lesser angle. So this theorem states a side which is opposite to the greater angle, side opposite to the 60-degree angle, which is BC, will be greater in length than the side which is opposite to the 27-degree angle, which is AB. So because 60 is greater than 27, that is sufficient for us to conclude that BC will be greater than AB. Right? So that's a fourth and final fundamental property of triangles that you need to remember. And of course, when we are talking about triangles, then we have to remember that basic formula for triangles area, which is half into base into height. We have to remember this as well. Right? Now, there's always a bit of confusion as to what is a height. People always misconstrue height and they confuse it with certain other constructions. So once and for all, let's clear that out, that any straight line which is drawn perpendicular to one side of a triangle from the opposite vertex is going to be a height. So if I draw the straight line from A perpendicular to BC, then this is going to be a height. That's all that needs to matter. That a height should be perpendicular to one side. It should be drawn from the opposite vertex. That's it. Okay. So these are the fundamental properties of triangles that we need to remember. Now let's look at relations. Or before that, let's look at classification of triangles. Right. So triangles can be classified into several different types, and we all know the classifications. I'm still going to run through it because we are making notes here. We're trying to consolidate all properties of quadrilaterals and triangles in one single place. So triangles can be classified based on lengths of sides. So based on the lengths of sides, we have got equilateral triangles. So what is an equilateral triangle? A triangle in which all three sides have the same length. Of course, we know this. So if in triangle ABC, AB, BC and AC are all equal, then it becomes equilateral in nature. Also, not just are all three sides equal, all three angles are also equal. And their values, of course, will be 60 degree. Why? Because sum of the three angles has to be 180. So each angle of an equilateral triangle will be equal to 60 degrees. Also, basic formula for finding out the height of an equilateral triangle, which comes up using trigonometry, is root 3 by 2 into A, where A is the length of the side of an equilateral triangle. And by extension, when we apply half into base into height for an equilateral triangle, I will get to know that formula for area of an equilateral triangle is root 3 by 4 into side square. Right. Okay. So that is the first type of triangle based on lengths of sides. Second type of triangle based on lengths of sides is an isosceles triangle. So an isosceles triangle, if I take a triangle like this, ABC, then if only AB and AC are equal, but BC is of a different length, then this kind of a triangle is called an isosceles triangle. And the non-equal side, which in this case is BC, is generally referred to as the base. Sometimes you might get a question which says that the length of the base of an isosceles triangle is equal to 2 centimeters. That basically means that the side which is not one of the two equal sides, the length of that side is 2 centimeters. Okay. And the property of all isosceles triangles is that both the angles with which the base forms, they both will be equal to each other. So BC is forming the angles B and angle C inside the triangle ABC. So these two angles will be equal to each other. That is a fundamental property for all isosceles triangles. And of course, the third and final kind of a triangle based on lengths of sides is a scalene triangle. And scalene triangle, of course, is when all three sides have different lengths, right? So equilateral triangle has all three sides equal, isosceles has two sides equal, scalene has all three sides of different lengths. Okay. Right. So this is the classification of triangles based on the measurement of the sides. Similarly, I can also classify triangles based on measurement of their angles. So based on measurement of angles, of course, let's go from smallest to the largest. Smallest triangles, of course, are going to be acute angles. So first type of a triangle is an acute angle triangle. So what's an acute angle triangle? A triangle in which all three angles are acute are called acute angle triangles. So that's all that you need to know about this type of a triangle. And when I say acute angle, acute means any angle which is less than 90 degrees. So when all three angles of a triangle are less than 90 degrees, then that kind of a triangle is called an acute angle triangle. Second type of a triangle is, of course, a right angle triangle, the one which is most famous when it comes to geometry. And this is something that we all know how to deal with already. Right angle triangles are triangles in which exactly one angle is 90 degrees. And of course, in this triangle, the 90-degree angle will be the greatest angle. And side opposite to the greatest angle has to be the greatest, which means this is the longest side. And we know that the longest side of a right angle triangle is referred to as the hypotenuse. And we also know that whenever we have a right angle triangle, we can apply the Pythagoras theorem. We see square, which says that the square of the length of the longest side will be equal to sum of the squares of the lengths of the remaining two sides. So square of the longest side is equal to sum of the squares of the remaining two sides. That is the Pythagoras theorem. And that is applicable only in the case of right angle triangles. So I think this doesn't need any kind of explanation. And finally, last type of triangle based on measurement of angles is an obtuse angle triangle. And an obtuse angle triangle is a triangle in which exactly one of the angles is obtuse. And when I say one of the angles is obtuse, I mean one angle is going to be greater than 90 degrees. So if I have a triangle like this, in which angle B is greater than 90 degrees, then this is an obtuse angle triangle. Now, just like in the case of a right angle triangle, obtuse angle of the obtuse angle triangle has to be the largest angle because sum of the three angles have to be equal to 180 degrees, which means that once again side which is opposite to the obtuse angle, this has to be the longest side. So this is going to be the longest side. And there's this very similar relation for longest side and remaining two sides for an obtuse angle triangle, just like how we have for a right angle triangle, with a small change within this relation. And the change is that for an obtuse angle triangle, square of the longest side will be greater than the sum of the squares of the remaining two sides. Okay. In the case of right angle triangle, square of the longest side will be equal to the square of the remaining two sides, or equal to the sum of the squares of the remaining two sides. And in the case of an obtuse angle triangle, sum of the squares will be greater than sum of the longest side, square of the longest side will be greater than the sum of the squares of the remaining two sides. Which means that, say, suppose I have an acute angle triangle like this, in which suppose, say, it doesn't look like it here, but suppose, say, I tell you that AC is the longest side. Then in the case of an acute angle triangle, square of the longest side will be less than the sum of the squares of the remaining two sides. So this is a relation of the square of the longest side and sum of the squares of the remaining two sides for all different types of triangles. Okay. So for an acute angle triangle, it will be less than, for a right angle triangle, it will be equal to, and for an obtuse angle triangle, it will be greater than. Right. So this is classification of triangles based on lengths of sides and based on measurement of angles. Moving forward, we will look at different relations that are possible between triangles. So first relation that we can establish between two triangles is, if say I've got two triangles on a plane, triangle ABC and triangle DEF, then sometimes you'll see questions telling you that ABC and DEF are equal. And we have to be very careful about this sign of equality, because several times students misunderstand this, because equality between triangles only denotes equality of area. That's it. It does not denote anything more than that. When I say that two triangles are equal, I do not mean their sides are equal or angles are equal or altitudes are equal, nothing of that sort. I only mean that the area that they're enclosing will be absolutely the same. So half into base into height for triangle ABC and half into base into height for triangle DEF will be equal. That is what is the meaning of this first relation of equality. Second relation that can be established between two triangles is given by this symbol, and this is the symbol for congruency. So this sign means that triangle ABC is congruent to triangle DEF. Now what does congruent mean? Congruent means that the two triangles can be superimposed on top of each other. So when I say superimposed, what I mean is, if I say pick up triangle ABC and place it on top of triangle DEF, then both of them will perfectly superimpose on top of each other, such that there are no surplus points on either triangle. So which means that I will not be able to differentiate between the two triangles if they are placed one on top of each other. So all points on triangle ABC will coincide with corresponding points on triangle DEF, so that if I just turn them around and I look at it from different sides, I will not be able to recognize any difference between them. That is what is the relation of congruency, that when two planar shapes can be perfectly coincided or can be perfectly superimposed on top of each other, such that all points on one shape coincide with corresponding points in the second shape, then the two shapes are said to be congruent. Okay, which means that when I say that two triangles are congruent, all their properties are going to be absolutely identical. So congruency is that relation which establishes the fact that the two triangles have equal sides, equal angles, equal areas, equal heights, equal angle bisectors. Everything about these two triangles will be the same. So they're absolutely identical triangles. That's what congruency as a relationship denotes. Now there are certain sufficient conditions to prove congruency. First sufficient condition to prove congruency, of course, is SSS congruency. So if I can prove that three sides of triangle ABC, AB, BC and AC are equal to the corresponding lengths of the three sides of triangle DEF. So which means if I can prove that AB and DE are equal, BC and DF are equal, AC and DF are equal, then this is sufficient for me to say that the two triangles will definitely be congruent to each other. Okay. So that's a first relationship or first way of proving, sufficient condition of proving congruency between two triangles. Okay. Second way of proving congruency between two triangles is SAS, which of course stands for side angle side. So if between two triangles I can prove that two sides are equal, AB and DE are equal, BC and DF are equal, and if I can also prove that angle B and angle E are equal, then this is also sufficient for me to say that the two triangles ABC and DEF will be congruent. Now there's one thing that we have to be careful about when we are applying the SAS congruency, is that we have to remember that SAS is always written as SAS, with the A as the central alphabet and two SS on either side. We will never write SAS congruency as SSA congruency or ASS congruency. Why? Because those are not sufficient conditions for proving congruency. So what do I mean by this is that, say, instead of proving angle B and angle E to be equal, instead if I had proven that angle A and angle D are equal, then this is no longer a sufficient condition to say that these two triangles will be congruent. Why? Because now it is SSA or ASS congruency, which is not a sufficient condition to prove congruency. So if you have to prove two triangles to be congruent by applying the SAS congruency, then remember that you have to prove that the angle which is included between the two sides that you're proving to be equal is proven to be equal, and only then can you say that the two triangles A, B, C and D, E, F are congruent to each other. Okay. So that is the second way of proving congruency between two triangles. And the third and final condition, sufficient condition to prove congruency between two triangles, of course, is AAS, stands for angle angle side. And good thing about AAS, which is not good thing about SAS, is that AAS can be written as AAS or ASA or SAA. It does not matter. Just that two angles and one side should be equal. It can be any two angles. It can be any one side. So then let's understand one thing here. So then does that mean that if I say that angle B and angle E are equal, BC and EF are equal, and then I say that angle C and angle D are equal, are then, or is this is it sufficient for us to say that triangle ABC and triangle DEF are congruent? No, this is not sufficient for me to say that the two triangles are congruent. Why? Because in the case of triangle ABC, it is ASA. In the case of triangle DEF, it is AAS. So sequence of the two angles on one side has to be the same. So if I have to prove that these two triangles are congruent, I have to either prove that angle C and angle F are equal, so then it's ASA for both, or I have to prove that angle A and angle D are equal, so that it's AAS for both. So sequence of the two angles on one side should be the same for both the triangles, and only then we can say that the two triangles are congruent by AAS congruency. Apart from this third condition, there is also a fourth condition to prove congruency between two triangles, but this fourth condition is applicable only in the case of right angle triangles, which is RHS congruency. RHS, of course, stands for right angle hypotenuse side. So between two right angle triangles, of course, right angles are going to be equal. If the length of the hypotenuse of both the triangles are the same, and if any one of the remaining sides is of the same length as well, then it is sufficient for me to say that the two right angle triangles will definitely be congruent to each other. Okay. So that is the second relation that you can establish between two triangles. Third and final relation between two triangles that is relevant to our syllabus, of course, is given by this symbol. And this is the dread of so many people when it comes to geometry, which is the symbol of similarity. So two triangles can be similar to each other. Right? What do I mean by similar? Similar shapes in geometry are basically shapes which are proportional to each other. When I say proportional to each other, it means that if I take, say, let me take some other shape. Let me take this shape. Okay, this shape. Okay. Now let me select this, and if I resize this, then this shape is similar to this shape, is similar to this shape, is similar to this shape. Right? Why? Because all these shapes are proportional to each other, just that they are of different magnified lengths. So it is basically, the word similarity refers to the similarity of shapes, that they are the shapes are similar, just that some are more magnified, some are less magnified. The same thing is true for triangles as well. That in case of a triangle, or in case of triangles, similarity is basically if I can take one triangle and I can just proportionally expand it to make it absolutely congruent to a second triangle, then the two triangles are said to be similar to each other. Okay. So if I have two triangles ABC and DEF like this, and if I want to prove that these two are similar, then what do I do? What does that geometrically mean? How can I quantify similarity? If that is a question that you're asking, then the condition that satisfies or which defines similarity is AAA. So when three angles of triangle ABC are equal to the corresponding three angles of triangle DEF, then they are said to be similar to each other. Now, whenever we have a pair of similar triangles, there are three or four properties, I would say, which we can apply to these to this pair immediately. Okay. Let me change this 3 to 3 for consistency. Yeah. Okay. So first property of similar triangles is that it's the same property of proportionality that we were discussing at the very beginning, that the sides of two similar triangles will be proportional. So ratio of the corresponding sides will be equal. Now the question is, what do you mean by corresponding sides? And that is what you need to focus on. That this word corresponding is very, very important when we are mentioning the first property of similar triangles. Ratio of corresponding sides are equal. So what do I mean by corresponding? What I mean by that is, if I look at this figure, angle A and angle D are equal, right? So A and D are corresponding vertices. Similarly, B and D are corresponding vertices, and C and F are corresponding vertices. So if I want to find out a pair of corresponding sides, and if I take side AB of triangle ABC, then corresponding vertex of A is D, corresponding vertex of B is E. So AB and DE are corresponding sides. Similarly, BC and EF are corresponding sides, and similarly AC and DF are corresponding sides. So ratio of corresponding sides is equal is this property. If you write instead that AB by EF is equal to AC by DF, this will become incorrect because AB and EF are not corresponding to each other. And this is something that leads to a lot of mistakes in similar triangles questions. That students apply the ratio of corresponding sides are equal before even understanding which the corresponding sides are. So please do not make that mistake. Please remember that you have to first successfully identify and recognize which the corresponding sides are before you apply this property of similar triangles. Okay, that's the first property. Second property of similar triangles is the fact that if I draw, say, two altitudes, if I draw an altitude from this vertex A, just a second, let me get this right. Yeah. From this vertex A, if I draw an altitude or height in triangle ABC, okay, let me call this, say, AP. And let me draw an altitude from D onto EF for triangle DEF. Let me call this altitude DQ. Then I can say that AP and DQ are corresponding altitudes of triangles ABC and DEF. And I can say that why? Because A and D are corresponding vertices. Right? So which means that I can say ratio of the corresponding altitudes of two similar triangles will be equal to the ratio of their corresponding sides as well. So AP and DQ, or AP by DQ will be equal to AB by DE, will be equal to BC by EF, will be equal to AC by DF. So ratio of corresponding altitudes of two similar triangles will be equal to ratio of the lengths of the corresponding sides. And this fact is going to be true for any other construction that you can make inside the triangles. So if I say draw the altitude from B and D, even those two altitudes will be the same ratio as the length of the sides. If I draw interior angle bisectors of angle C and angle F, then those two interior angle bisectors will also have the same ratio as that of AB by DE, BC by EF, and AC by DF. Why? Because that is the definition of similarity. That all constructions within these figures which are similar to each other will be proportional to each other. And they will have the same proportionality. That is what is the definition of similarity. Third property, which I don't like mentioning inside the class, but then it is something that students need to understand and that can come in handy in so many questions, is that even perimeters of, or the ratio of the perimeters of two similar triangles will also be equal to the ratio of the lengths of the corresponding sides. And it is obvious. Once again, by the concept of proportionality, it is obvious that the ratio of the perimeters of two similar triangles will be equal to the ratio of the lengths of the corresponding sides as well. Okay. Simple, you have to do addendo. Remember surds, if you apply the concept of addendo from surds to the ratio of corresponding sides are equal, you will come to the fact that perimeters ratios of two similar triangles will also be equal to ratio of the lengths of the corresponding sides. And fourth and final property of similar triangles is that ratio of the areas of two similar triangles, and this is also kind of instinctive and obvious, ratio of the areas of two similar triangles will be equal to ratio of the squares of the corresponding sides. So these are the four properties of similar triangles. Okay. Now apart from these, I would like to discuss some sufficient conditions to prove similarity between triangles as well. So if I want to prove that ABC and DEF are similar, what else or what conditions need to be satisfied? So first condition that needs to be satisfied, that can be used to prove similarity, is AA. Right? Because if two angles are equal, of course the third angle will be equal. Right? Because sum of all three angles of a triangle will be equal to 180 degrees. So if two angles are equal, third angle will be equal. So that is a sufficient condition to prove that the two triangles are similar to each other. Second sufficient condition for similarity is what is this itself. If I can prove that ratio of all three side lengths are the same, then that is sufficient for me to say that the two triangles will definitely be similar to each other. Okay. So if nothing about the angles is given, but lengths of sides of both the triangles are given, and if you can observe that, hey, look at this, the ratio of the sides are equal, then that means that the two triangles will definitely be similar to each other. Okay. And finally, there is a third way of proving similarity, which is very similar to SAS congruency. applied to similarity basically. So for that, say suppose I take two triangles like this. I call one triangle XYZ. I call one triangle PQR. And suppose in the question that I have in front of me, it says that angle X and angle P are equal. But no other piece of information about angle Y or angle Z or angle Q or angle R is given to me. But what has been given to me is the length of XY has been given, length of XZ has been given, length of PQ and PR have also been given. And suppose I can observe that XY by PQ is equal to XZ by PR. Then this is also a sufficient condition to prove similarity. So what's a sufficient condition? One angle between two triangles are equal, and the two sides which are forming that equal angle are in the same ratio. Then this is also sufficient for me to say that triangle XYZ and triangle PQR will be similar to each other. Okay. So this is the third and final sufficient condition to prove similarity between two triangles. Okay. Right. So this is the fundamental properties of triangles. Apart from these, there's one more property which comes in handy in several questions. I'm going to say one, I will call it two, but both of them can come under the same umbrella of being trigonometric properties. So the two properties, of course, that I'm talking about are sine rule and cosine rule. So why do we need to know sine rule and cosine rule? Trigonometry is not exclusively part of a syllabus, but still it is important for us to understand basic trigonometry. Why? Because sometimes in triangles questions, you will be given hybrid data. You will be given data as a hybrid of both lengths of sides and measurement of angles. And till now, whatever concepts that we have dealt with or that we have looked at within this video have either dealt with lengths of sides only or with measurements of angles only. But sine rule changes that. It gives us a relation between sides and angles of a triangle in the same equation. So that's why these two rules, sine rule and cosine rule, are very important, because if a sense of hybrid data with respect to triangles is given, if lengths of sides and measurement of angles have been given, then probably we should immediately think about sine rule or cosine rule. Okay. So for that, so to get a sense of understanding of what sine rule is, let's take a triangle ABC. And let's say the length of the three sides are small a, small b, and small c, such that small a is the length of the side opposite to capital A vertex. Small b is opposite to capital B, small c is opposite to capital C. Then sine rule says that a by sine of angle A is equal to b by sine of angle B is equal to c by sine of angle C. And cosine rule for triangle states that cos of angle A is equal to b square plus c square minus a square by 2bc. Cos of angle B is equal to a square plus c square minus b square by 2ac. And cos of angle C is equal to a square plus b square minus c square by 2ab. Right. So these rules will come in handy in solving questions wherever hybrid data is given with respect to a triangle, where data is given with respect to lengths of sides and measurement of angles, and you have to combine them, contrast them, find out something else, some other parameter inside a triangle, turn to sine rule or cosine rule. Right. Okay. Now that this is clear, now finally for triangles, we'll be looking at significant constructions that we can make inside a triangle. So first significant construction that we can make inside a triangle is, of course, its altitude or its height. So what is an altitude? Again, to make it very clear, altitude is the perpendicular dropped from one vertex of a triangle onto its opposite side. Okay. So let's be very, very clear about this. It is not any other thing. No midpoint, nothing is there. Okay. Just that perpendicular drop from one vertex onto the opposite side is called an altitude. And since there are three vertices, I can draw three altitudes. So I can draw an altitude from B, and I can also draw an altitude from C. So I've got three altitudes always in a triangle, and the three altitudes of a triangle will always be concurrent. So what do I mean by concurrent? Concurrent means they will all pass to the same point. And this point of concurrency of triangles is called the triangle's orthocenter. So if I denote the orthocenter by the letter O, then property of a triangle's orthocenter is that the angle which the triangle's orthocenter subtends with two vertices and the angle subtended by those same two vertices at the third vertex, they will always be supplementary. So I know that this language is very confusing. Let me write it down for you to get a better sense of understanding. So if I take angle BOC, this angle is an angle subtended at the triangle's orthocenter by the vertices B and C. B and C subtend an angle BAC at the third vertex. So these two angles will be supplementary. Similarly, in this figure, I can say angle AOB plus angle ACB will be supplementary. And I can say angle AOC plus angle ABC. This will also be supplementary. So this is what we have to understand about a triangle's orthocenter, right? First construction of significance that we can make inside a triangle. Okay. All right, so let's move on. Moving on. Second construction of significance that we can make inside a triangle, of course, is a median. So median is constructed by joining one vertex with the midpoint of the opposite side. So if I take this vertex and if I join it with the midpoint of the opposite side, and if we call this triangle ABC, then AD will be the median of triangle ABC. First thing to remember about medians is that a median will divide a triangle's area into two equal halves. So triangle ABD's area and triangle ADC's area will be equal. And each of these triangles' area will be half of the area of triangle ABC. Okay. Second thing, which most people forget as soon as it comes to a question of medians, is that whenever there is a median inside a triangle, you can apply one very famous theorem, which is called the Apollonius theorem. So whenever there's a median inside a triangle, you can apply the Apollonius theorem. And what does the Apollonius theorem state? So if this is a triangle and AD is a median, then Apollonius theorem states that AB square plus AC square is equal to 2 into BD square plus AD square, where AD is a median of triangle ABC. Now this is as important as the Pythagoras theorem, right? Because if you see a right angle triangle, immediately you think of the Pythagoras theorem. But for some reason, students tend to forget that as soon as you see a median inside a triangle, you should think about Apollonius theorem and you should ask yourself that is this going to be relevant to the solution of the question or not? Because several times if a median is given and some other length has been asked, Apollonius theorem is what you would turn to solve the question. Okay. So whenever there's a median, you can apply the Apollonius theorem to that particular question. Okay. Also, just like a triangle's altitude, a triangle will have three medians. One will be drawn from B, one will be drawn from C, one will be drawn from A. Right? And the medians of a triangle will also be concurrent. Concurrent means they will also intersect each other at one point, and this point of intersection of the medians is called centroid of a triangle. And centroid will always be denoted by the letter G. Why G? Because anyone who has studied science 11th and 12th should understand that centroid is where the center of mass of the triangle lies. And that's why G, because center of mass or center of gravity of a body in physics is always denoted by G. And the property of the centroid is that a centroid divides all three medians in the ratio of 2:1. So if I take this median AD, then this point G, it divides this length AD in the ratio of 2:1, and the two part will be near the vertex and the one part will be near the base. Same thing will be true for the median drawn from the point B. Same thing will be true for the median drawn from the point C. Centroid divides all three medians with the same ratio of 2:1. Right? That is the second construction of significance that we can make inside a triangle, which is a construction of a median. All right. Moving forward. Third construction of significance that we can make, of course, is interior angle bisector. Okay. So what's an interior angle bisector? So the name itself is sufficient for us to understand that the interior angle bisector is any straight line which bisects an interior angle of a triangle. So if I draw a straight line like this in triangle ABC, such that angle BAD and angle DAC are equal, then AD is an interior angle bisector of triangle ABC. And whenever there's an interior angle bisector, just like whenever there's a median, we can apply the Apollonius theorem. Similarly, whenever there's an interior angle bisector, I can apply the interior angle bisector theorem. And this theorem states that AB by AC will be equal to BD by DC. This equation is again very important. Why? Because this is probably the only other relation which deals with ratios of lengths apart from similar triangles concept. So if there's a ratio based question in geometry and you are not being able to understand that you feel that there's no similar triangles inside this question, but you still have to find out some ratio, then maybe you have to check for interior angle bisector theorem application as well, right? So interior angle bisector theorem states AB by AC is equal to BD by DC. All right. Also, just like medians, just like altitudes, there are going to be 3 interior angle bisectors inside a triangle. And the interior angle bisectors of a triangle are also going to be concurrent. And this point of concurrency is called, if I call this I, is called the triangle's in center. In center is the meeting point of interior angle bisector. Simple to understand. In. Okay. And the property of an interior angle bisector is that, or property of the triangle's in center is that from this in center, if I drop perpendiculars onto the 3 sides, right? If I say drop a perpendicular onto AC, if I drop a perpendicular onto BC, and if I drop a perpendicular onto AB, okay, suppose these 3 are perpendiculars. And let me call these perpendiculars from I onto AB, BC, and AC as say IX, IY, and IZ. Then property of these 3 will be that Ix will be equal to Iy will be equal to Iz. So perpendicular distance of the triangles in center from the 3 vertices will always be equal. Okay. What this means is that if I take this point I as a center, and if I take any one of these 3 lengths as a radius, then I can draw a circle like this, which will be perfectly inscribed inside the triangle. And such a circle is called the triangle's in circle. And the radius of this circle, which is Ix, Iy, or Iz, is referred to as a triangle's in radius. All triangles will have one in center, one in circle, and one in radius. In radius of a triangle is generally denoted by small r. And the formula for finding out the value of small r is delta by s, where delta is the triangle's area, s is the triangle's semi-perimeter. Okay. Fourth construction of significance that I can make inside a triangle, or actually before that, there's one more property of the triangles in center, which is very similar to the property of the triangles orthocenter that we had discussed, right? So if I take this point I, then B and C are subtending an angle BIC at this point I. So B and C are subtending angle BIC at the triangles in center. And the value of this angle will be 90 more than half of the angle subtended at the third vertex. Similarly, A and B subtend angle AIB at the triangles in center. This will be 90 more than half of the angle subtended at the third vertex. And similarly, angle AIC will be 90 more than half of the angle ABC. So this is one more property of the triangles in center. That's a third construction of significance that we can make inside a triangle. Okay, moving on. The fourth construction of significance that I can make inside a triangle is an exterior angle bisector. The first question that I generally ask students inside the class as soon as this exterior angle bisectors is that how many exterior angles are there in a triangle? And several students forget to take into consideration several cases of constructing exterior angles. Right? Exterior angles are formed by producing a side and forming an angle with an existing side. So there are in fact 6 exterior angles inside a triangle. Why? Because I can form 3 exterior angles like this by producing the sides in a clockwise direction. I can form 3 more like this by producing the sides in the counterclockwise direction. Right? So what that means is that this is an exterior angle, this is an exterior angle, these two are exterior angles, and these two are exterior angles. Okay. So when I'm talking about exterior angle bisectors, those are straight lines which are going to bisect exterior angles. And there are going to be 6 exterior angle bisectors, right? So one is going to bisect this angle, one is going to bisect this angle, one is going to bisect, one is going to bisect this angle, this angle. My constructions are not going to be up to scale, so pardon me for that. So all of these are exterior angle bisectors. So this line is going to bisect, sorry, just give me a second. So this line is going to bisect this angle. This line is going to bisect this angle. This line is going to bisect this angle. Similarly, this is going to get bisected. These are going to get bisected, and this is also going to get bisected. So exterior angle bisectors. And if I look at this figure, this looks like a very big hodgepodge of a figure. So that's why exterior angle bisectors are not very important as far as CAT as a paper is concerned. But there's one property of exterior angle bisectors which you have to remember, is that you can see that there are clearly 3 distinct points at which exterior angle bisectors meet or cut each other. And if I call these 3 points as E1, E2, and E3, then these 3 points are called the excenters of triangle. So E1 and E2 and E3 are excenters of triangle ABC. And property of the triangle's excenter is the same as the property of the triangle's incenter, which is that from any of these excenters, if I take E2, from E2, if I drop a perpendicular onto AC, and then I drop a perpendicular onto AB produced, and similarly, if I drop a perpendicular onto BC, and if I take the lengths of these 3 perpendiculars, then these 3 perpendiculars will be equal in length. So just like a triangle's incenter, the perpendicular distance of a triangle's excenter from the 3 sides of a triangle will also be equal. What this means is that if I take, once again, if I take E2 as a center and any one of these 3 perpendicular lengths as a radius, then I can construct a circle like this such that the 3 sides of a triangle will be tangential to the circle as well. And this circle is called the excircle of a triangle. And since a triangle has got 3 excenters, it will have 3 excircles as well. And these 3 perpendicular lengths are called x radius. So all triangles are going to have 3 x radii as well. So this is something that you need to know. This property can actually come in handy in certain questions. Remember that all triangles have got 3 excenters, which means all triangles have got 3 excircles, and all triangles have got 3 x radii. Okay. Apart from this, there's an exterior angle bisector theorem, which hardly ever comes into play inside CAT-based questions. I'm not going to go into that and confuse people. So even without that, you can actually get a decent score inside the CAT paper. So you need not know anything more than this, but this much basic concept of exterior angle bisectors we need to know, because it can make some questions very simple to solve. Okay. And finally, the fifth and last construction that we can make inside a triangle is the construction of a perpendicular bisector. So perpendicular bisector, as the name itself suggests, is a straight line which is perpendicular to and bisects a side of a triangle. So if I have a triangle ABC, and in this triangle, if I say draw a straight line like this, Draw a straight line like this, passing through the midpoint of BC and perpendicular to BC. Then this straight line is a perpendicular bisector of triangle ABC. And since a triangle has got three sides, I can draw three perpendicular bisectors, right? I can draw a straight line which is a perpendicular bisector of AB. I can draw a straight line which is a perpendicular bisector of AC. So all of these are perpendicular bisectors, and the perpendicular bisectors of a triangle will also be concurrent. And this point of concurrency of perpendicular bisectors is called the circumcenter of a triangle. And property of the circumcenter, say if I take this circumcenter as C1, then property of the triangle circumcenter is that the distance of the circumcenter from the three vertices are equal. So if I join C1A, C1B and C1C, then C1A, C1B, C1C will all be equal. And what this means is that if I take C1 as a center, if I take the circumcenter as a center and any one of these three distances as a radius, then I can construct a circle like this, which will perfectly circumscribe the triangle. And this circle is called the triangle circumcircle. And the radius of this circle, which is C1A, C1B or C1C, is called the circumradius of triangle ABC. Okay. And circumradius of a triangle is denoted by capital R. And the formula for finding out the length of capital R is given by ABC by 4 delta, where A, B and C are the lengths of the three sides of the triangle. And delta, of course, is still going to be the triangle's area. Okay. So product of the three sides of a triangle divided by 4 times the triangle's area is how we calculate the length of the circumradius. So these are the significant constructions that we can make inside a triangle. All right. So if this is clear, we'll finally look at certain special conditions or special cases of these significant constructions of triangles. So first special case of significant constructions happens to be in the case of an equilateral triangle. So what happens inside an equilateral triangle? Speciality of an equilateral triangle is that if say this is an equilateral triangle, and if I draw an altitude of this triangle like this, say let me call this altitude AD, then AD will not just be its altitude, AD will also be its median, will of course will be its perpendicular bisector, and will be its interior angle bisector as well. So for an equilateral triangle, altitude, median, interior angle bisector, perpendicular bisector are all the same straight line, okay, which means that for an equilateral triangle, orthocenter, centroid, incenter and circumcenter are going to be the same point. So that is speciality number 1, which happens in the case of an equilateral triangle. Second speciality, second special case happens to be in the case of an isosceles triangle. So in an isosceles triangle, if I take this triangle ABC, suppose AB and AC are of the same length, then there are two specialities to this. First speciality, let me call it 2.1. Okay. So in this isosceles triangle, if I draw an altitude from this vertex A, now this vertex A is special. Why? Because it is common to the two equal sides. So if I draw an altitude from the vertex which is common to the two equal sides of an isosceles triangle, then this altitude will not just be the altitude, this will be median, interior angle bisector and perpendicular bisector. But this will be true only for the altitude drawn from the vertex which is common to the two equal sides. This will not be true for the altitudes drawn from the base vertices of B and C. So the median, altitude, interior angle bisector and perpendicular bisector drawn from the vertex which is common to the two equal sides of an isosceles triangle will be the same straight line. Okay. That is the first speciality. For the second speciality of isosceles triangles, let me do one thing. Let me consider the same isosceles triangle, ABC once again, where AB and AC are the equal sides. And suppose in this triangle, I draw the altitudes from B and C. Okay. Then, and let me call these two sides, say these two altitudes are, I'd say, BE and CF. Then second speciality says that BE will be equal to CF. So the altitudes drawn from the base vertices of an isosceles triangle will be equal. Okay. That's the second speciality. Now say suppose I tell you that B and CF are not altitudes. They are in fact interior angle bisectors drawn from the base vertices. Even then B and CF will be equal to each other. Now suppose if I tell you that no, B and CF are not interior angle bisectors. They are medians drawn from the base vertices. Even then B and CF will be equal to each other. So any special construction that you make from the base vertices of an isosceles triangle, be it altitudes, be it medians, be it interior angle bisectors, they will be equal in length to each other. Okay, that's the second speciality of all isosceles triangles. And the third and final special case of significant constructions inside a triangle happens to be in the case of a right angle triangle. So what happens in a right angle triangle? Firstly, the triangle's orthocenter is present at the vertex B. Right? Why? Because orthocenter is what? Meeting point of the altitudes of a triangle. What is an altitude? Perpendicular drawn from one vertex onto the opposite side. So if the opposite side is BC, altitude is AB. If the opposite side is AB, altitude is BC. So both the altitudes are meeting at B. So B becomes the orthocenter of triangle ABC. So in a right angle triangle, orthocenter will always lie at the vertex containing the right angle. And second speciality of all right angle triangles is that circumcenter of a right angle triangle will always lie at the midpoint of the hypotenuse. So this becomes C1. Midpoint of the hypotenuse is where circumcenter of all right angle triangles lies. Which means that if I want to find out the value of circumradius of a right angle triangle, all I need to do is divide the hypotenuse by 2. I don't need to apply the formula for circumradius, that ABC by 4 delta and all. I don't need to do. Just find out the triangle's length of the hypotenuse and then divide that by 2 and you will get the value of circumradius of right angle triangles. Now the most interesting thing to note about these two specialities of right angle triangles is that circumcenter and orthocenter of a right angle triangle are lying on the perimeter of the triangle. What this essentially means is that in the case of an acute angle triangle, these two centers will lie inside the triangle. And in the case of an obtuse angle triangle, these two centers will lie outside the triangle. So the position of circumcenter and orthocenter can actually help us determine what type of a triangle we are dealing with. If in a question, the circumcenter and orthocenter are present inside the triangle, that's an acute angle triangle. If it is on the perimeter of the triangle, it is a right angle triangle. If it is outside the triangle, then it's an obtuse angle triangle. Whereas the remaining centers, which are centroid and incenter, will always lie within the triangle for all triangles. And the excenters, of course, will always lie outside the triangle for all triangles. Okay. So these are the basic properties of triangles and quadrilaterals. So this is a lot to deal with. And I can understand why several students find geometry difficult to deal with. So that's why I made this video, because you need not always keep on scouring through different places to find out formula and concepts. This video is basically made for you to make note making for yourself, making notes for yourself much more easier. So please use this video to make notes. Also, please don't sit and mug up all these concepts. I'm asking you to make notes and consolidate all these concepts into one single place so that you can refer to them while you're solving questions. Practice is the most important thing that you can do to excel in geometry based questions. So practice as many questions as possible. And whenever you're practicing, keep your notes open in front of you so that you can refer to whatever figure has been given. You can refer to the relevant concepts that you can pick up from that notes and apply it. And let practice be the reason why you recollect and remember all the concepts properly. Okay. So that is it with today's session. A similar session I will again make with respect to circles and polygons as well, so that you can make a note of properties of circles and polygons as well, and make a comprehensive consolidated notes of all the concepts that is required for solving questions of geometry. Right? So thank you everyone for watching the video and have a good day.